Let's look at one more example, and then you guys can choose to pause and kind of do the homework for Monday and then come back to the video for Tuesday's homework, or you can watch it all in one sitting. It's up to you. I'm going to zoom back in. All right, I think that's good. So this example says, use inverse trig functions to write theta as a function of x. So it doesn't say to evaluate theta, it just says write theta as a function of x. So what that means is I have theta and I need to write it as some function where x is my independent variable. Okay, so then I'm looking basically for an expression or an equation for theta. I'm not looking for a value. So I look at this triangle and say, okay, well, what do I know about theta? What do I know about this triangle that would allow me to write an equation? And we look and we say, well, what I know is, I know theta is here. I know that the opposite side to theta is equivalent to the expression x plus 1. Now, we don't know what x plus 1 is. We don't even know what x is. But we know that the expression x plus 1 is equivalent to the side length here. And then I also know that my adjacent side is 10. Right? And then I look and say, well, I know where theta is. I know what the opposite side, the expression for it is. I know the adjacent side's value. What trig ratio can I use to write an equation? Well, if we think of SOHCAHTOA, I'm going to put that here. Right? The ratios for sine, cosine, and tangent. The only one that uses opposite and adjacent would be tangent. So I'm going to say, well, I can write an expression with tangent. Tangent of theta equals opposite over adjacent. And for our purposes, our opposite side is x plus 1. Our adjacent side is 10. This would be nice and done if I were asked to write just any old expression. But it actually says write theta as a function of x. So what that means is theta needs to be isolated. So I'm going to write here, isolate. Right? And how do I get theta by itself? It's kind of trapped in that tangent. Well, inverse functions, right? That's why we're kind of looking at these inverse functions so that later on when we do our applications, we can get just the angle if that's what we're looking for. So all I'm going to do is use the inverse on both sides. Tan inverse of tan theta. So I just wrote what I had on the left side, and then tan inverse of what I had on the right side. And what that does for me is tan inverse and tan cancel each other out, right? They're inverses of one another, so they cancel each other out. And now I have theta by itself, and it equals tan inverse of x plus 1 over 10. So now I have an expression for theta where x is my independent variable. So I've written theta as a function of x. And again, tan inverse and arctan are the same thing. So you could write this as theta equals arctan of x plus 1 over 10. I'll put here or. Either of these two answers are acceptable. Alright, so that takes us at least until most of Monday's work. So you can stop the video here, or you can keep going on. The rest of the work is for the end of Monday's homework and then Tuesday's work. Alright, so here it does say evaluate the expression, so that means we should get a value. Right? When we see this word value, evaluate, that means I need an actual value, a number value for my answer. It shouldn't be just an expression, but it should be an actual value. So if I look here at tan of arctan of 25. So we know order of operations, we're going to work in the inner parentheses first and then expand out from there. And this is truly a composition of functions. I have a function here, right? Arctan is an inverse function, and I'm taking that answer and plugging it into another function. So we looked at compositions before. We know that we take the answer from one function and plug it in as our x, or our value, our independent variable, into the outer function. So I'm going to rewrite this as theta. We know that arctan, just by our definition of anything, in this case of 25, is asking us, well, what's the theta, what's the angle measurement where I were to plug in tan of that angle, I would get 25. So I'm going to come over here, do a little scratch work and say, I'm looking for tan of theta, because this expression is theta, whatever the angle is. Okay. But what do I know about theta? Based on arctan 25, I know that tan of theta equals 25. That's exactly what this expression means. We said for arctan, we can rewrite it as just regular tan of theta equaling that measurement of 25. Then when I come back here and say, okay, well, this is what I know about theta, what are they asking me? They're asking me for tan of theta. I already know the value from here. So my answer is just 25. That's the beauty of inverse functions. I have tangent, I have its inverse, they cancel each other out, and I just end up with the value of 25. Okay, so tan of arctan of 25 is just the value of 25. I'm going to do the same thing here. Only difference is I won't be able to just cancel out tan and arctan or sine and arctan because they're not inverses of each other. This would actually have to say sine for me to do something like that. Right? So right now, I'm just going to go with the same steps, look at the inner parentheses and say, okay, arctan of 4/3. I don't know what that is, but I know the answer is some angle, so I'm going to call it theta. And what I'm asked to do is find sine of theta. What do I know about theta? Well, from here, I know that tangent of theta equals 4/3. Tangent of theta equals 4/3, based on what this inner parentheses is telling me. And then I say, okay, well, I still don't know much about theta, but now I know the ratio of tan is 4/3. So I know tangent is opposite over adjacent, which means if I were to draw a little right triangle and I put my theta here, the opposite side would be 4, the adjacent side would be 3. Now I'm asked about sine, and sine is opposite over hypotenuse. So I actually know some information. I know the opposite side is 4, and I can use Pythagorean theorem to figure out what the hypotenuse is. I'm going to call this h. All right, so we say, okay, Pythagorean theorem says a squared plus b squared equals c squared. If I go through and plug in, I have 9 plus 16, which is 25, equals h squared, and then I can square root both sides and I get that 5 is h. So that means my hypotenuse is 5. Of course, this was a 3, 4, 5, so you didn't really have to do Pythagorean theorem for that one, but just to show where the 5 is coming from. So now we know that sine of this theta equals opposite over hypotenuse, which is 4/5. So sine of arctan of 4/3 equals 4/5. All right, and then our last two examples, almost the same thing except we're not evaluating anymore. We're just writing an expression, right, that's equivalent to the given expression. So that means I'm not going to find a value like 25 or 4/5. I'm just going to find another expression. Right? I haven't been given enough information to find a value. I'm just rewriting it in maybe a simpler expression. So again, I look at the inside and I say I'm looking for sine of arctan of x. So again, I'm going to call this theta and say that I'm actually looking for just sine of theta. All right? And then I say, well, okay, what do I know? Well, if I bring this over here, arctan of x equals my theta. So that means that tangent of theta equals x. Tangent of theta equals x. And again, just like we did before, I know that tangent is opposite over adjacent. So I'm going to put this over 1. Opposite over adjacent, which means if I look at my triangle, and let's put theta here, I know that the opposite side is x and the adjacent side is 1. I can figure out what h is and use that to figure out what my sine is. Because again, sine is opposite over hypotenuse. I already know the opposite side is x. I got to figure out what the hypotenuse is so that I can plug it in here. So Pythagorean theorem, a squared plus b squared equals c squared, which is my hypotenuse. This one I really don't know what x is, so all I have is 1 plus x squared equals h squared, and if I square root both sides, I'll get the square root of 1 plus x squared. Can't simplify anything there because of that addition, equals my hypotenuse. So now I can come over here and say, okay, sine of theta is opposite over hypotenuse, which is x over square root of 1 plus x squared. Use my inner parentheses to plug in a value to my outer function so I can find my final answer. All right, so I'm going to write that here because it's a little bit squished in. So we had x over 1 plus x squared, and there's a square root over all that. All right, let's try one last one. So we're looking for cotan of arctan of 1 over x, right? So a nice thing is I can't cancel these out because they're not inverses exactly of each other, but cotan and tan are related in another way. So let's just start out with rewriting this as theta. So I'm really looking for cotan of theta, and I think about cotan as, well, cotan is adjacent over opposite. So I'm looking for that ratio. So let's go to our side, do a little scratch work, and say arctan of 1 over x means that tangent of theta is 1 over x. Tangent of theta equals 1 over x. Right? So again, we know that tangent is opposite over adjacent. I could stop there and I have my answer, but we can keep going and say, okay, here's my theta. I know the opposite side is 1. I know the adjacent side is x. Kind of like the triangle that we had previously, we just switched sides a little bit. And so because cotangent doesn't ask me about hypotenuse, I really don't care about the hypotenuse at all. I care about the adjacent side and the opposite side of theta. So adjacent is x, I'll put here x, over opposite side is 1. So I have cotan. I didn't have to do any Pythagorean theorem for this one. Cotan of theta equals x over 1, which we can simplify down to just x. So our task was to write an expression equivalent to the given expression, so x would be equivalent to our given expression. Okay, so that wraps up section 4.7. Just kind of use the videos that I've posted, use this to kind of help you out, and of course, when we meet on Wednesday, you can ask questions.